Hello folks again. So now we have our second big presentation by Edward Kmett. I don't think Edward needs to be introduced, so let's keep it short. Take it away.
Thank you. So I was at Yao Lambda Jam last year, and Declan Conlon gave a talk on Fritz Henglein's work on discrimination, and I skipped the talk and didn't notice it until I went back down to Sydney, and he was giving a talk right before me, and I said, I should go watch his old talk. So I went and mined through the papers and found the old talk, and I said, oh, there's this wonderful thing I can do to build a library in Haskell that hasn't been written yet. And so now I have a new library, and I wanted to talk a bit about it and play with some people's preconceptions about how long it takes for doing a number of operations like sort and nub and these things in Haskell. Okay, and so the name here is a bit of a lie, or a bit of a distraction. What discrimination here is actually a technical term, not the sort of social good term that some people might have been misled into thinking I was going to talk about. The idea of discrimination is that what I want to do is I want to provide a generalized form of sorting and partitioning that we can define generically. We're gonna use this more or less as an exercise in optimizing Haskell code again. So kind of in the same vein as Duncan's talk the other day, using somewhat different tools. And how many people here are familiar with the notion of a radix or a bucket sort? Okay, good. So about 50%, 60%. So the idea of a radix sort is that, well, unlike what many people have taken away, but not quite what was said during your algorithms classes and the like, sorting doesn't necessarily have to take n log n time. Sorting based on pairwise comparisons has to take n log n time. But if you had something where, like if you wanted to sort integers, and you had one bucket per integer, you could go through and take each one of your integers, put them into the appropriate bucket, just bump the counter or whatever you're going to put there, or const onto a linked list that you put into that bucket, and then you could run through all the buckets in order and spit out your answers. And this doesn't care how many numbers you have, just the number of distinct integers. It just cares about the space of equivalence classes of integers that you have, the number of distinct buckets that you have. The buckets kind of take over for that log n factor that we had before. Okay. Now, the notion of a radix sort is what you do is if you wanted to sort integers, you would look at the least significant byte of your integer, and you would break things into buckets by that, and then if you break by then you gather those up, break by the next most significant byte, gather that up, break, gather it up, break. And by the time you're done, you have sorted by your integers stably, keeping all of the properties that we want, but we've now done a sort in O(n) time. That's the notion of a radix sort, is that you kind of work your way bottom up through something kind of a fixed shape. Back, is it 1990 or so, I think Burke, McIlroy, and Burke did a paper on how to make radix sort fast. And what they built was a sort of top-down radix sort, where normal radix sort goes bottom up. They came up with something called an American flag sort. And the American flag sort is, what we're going to do is we're going to break things into buckets, and then we're going to zoom in on one of the buckets and continue to sort using the same kind of techniques until we're done at the leaves. And so the nice thing about this sort of top-down approach is that it can stop work the moment you get down to a bucket of size 1, right? You don't have to keep walking down. Whereas with the normal radix sort, you have to do 1 bin per level and you have to pay for everything. And the nice thing about that sort of American flag technique is that we're going to show that we can now start applying it to things like ADTs. Okay, so this is a high level, actually a fairly low level, overview of what my goal is to make a nice, efficient library for doing sorting and partitioning and grouping and all these things. For pretty much anything you want in Haskell, just by breaking that assumption that we have to do everything pairwise. All right? So let's try and do everything in linear time. Sorting, partitioning, joining tables, constructing maps and sets. You know, everything that we've kind of conditioned ourselves is in log n or worse. And the ideas here come from a guy, Fritz Henglein. He's the director of the Hyperfit Research Center over at Copenhagen. He's a really nice guy. And he's written a bunch of really nice papers on this topic. And I haven't heard too much about it by anybody except for him. So he gave a couple of wonderful talks on the topic, and then it kind of went quiet. So I'm going to try and build a nice API on top of this. And you know, whenever you start talking about data structures, I think the first thing that goes through everybody's mind is that monads are monoids in the category of endofunctors. What's the problem? So I'm going to take a very long digression into the very definition of a monoidal category and where monads come from. And we're going to see if we can use this to build a nice API for sorting. Okay? So, what is the problem? We have this definition of a monoid in Haskell. And it's not the most general definition that we can give for a monoid. Okay, so what I really want is a place to sort of define my monoid. So I need this thing called a monoidal category. And we're going to wind up with this kind of crazy construction where we have some kind of bifunctor on our category. How many people here know what a category is? Let's start there. Okay, so I'm sorry to everybody in the newcomer section. I'll try to make it swift. So a category is basically anything where you have objects and arrows that go between objects such that you can compose arrows heads to tail, and at that point in time, if that's all you've got, you're going to get lost. I'm sorry. So a monoidal category is a category where we've added a bifunctor, something that acts like product or coproduct. So comma or either. And we have some object that's, with respect to this bifunctor, a unit. That basically, it adds or removes no information to put it on the left or the right using my tensor. So a tensor I is isomorphic to I, and I can go back and forth between these two things. Okay? And I have the ability to reassociate things in my bifunctor. Now this, if you squint at it, there's something kind of monoid-like going on here. So a monoid just gives us an associative operation and unit loss. And then we get these sort of crazy diagrams, which are being clipped off. Oh, on that screen it's being clipped off, but it works on this one. Good. Look at one of the monitors that does have it if you got clipped. All right. And these side conditions are basically, once you try to categorify the notion of a monoid, you need some extra conditions. So this is basically says that I need to make sure that if I associate all the way to here, I get the same answers if I, in either way that I can get there. And then the other condition is just that lambda and rho do kind of the same thing. The names here, rho is for R, for right. It's putting on and taking out the unit on the right. Lambda is for L, for left. It's not my naming. Mathematicians. Okay, so the first definition of a monoidal category that we have is this notion of the category of Haskell data types, where in our category, our objects are our types, and our arrows are functions that go from this type to that type. Okay, and so we can compose two arrows as long as the head and the tail of the arrows that we're composing agree. We're just a composition of functions. Okay, and here, what we need is the ability to, we need some kind of tensor, some kind of thing that we can glue together values with, or types with. And here I'm going to choose the tensor to be product. And the unit for product is a unit. Okay, not terribly surprising there. So rho can put on and take off something from the right-hand side. We can just use first to project out A, leaving the unit behind. There was no information in the unit. I mean, we could hide a bottom in it because we're in Haskell, but whatever. And we can just put a unit back if we want to go backwards. So we can go in either direction with row, and we can go with either direction on the other side. And it's not a terribly complicated exercise for the reader to write a function with this type signature. You just cover up the colon. Okay, and that is the body as well. And then products, we can also have coproducts. I used plus for space, it's either in normal vocabulary. And so we can say that the inverse of this is to put left on. But then what we need is, we need something such that either A or that is isomorphic to A. And so we'll use an uninhabited data type, which we have called void, which moved into base, I think, in 7.10. We just did it, so yay. And it was previously available in the void package. And this is just a unit for either, if we pretend that bottoms don't exist and do nice things. And so we can reassociate eithers as well. Okay? And I'm looking for another example of a monoidal category, which is, we can go build a category where our objects are functors, and then our mappings are these things called natural transformations, where a natural transformation says, basically, for all of the possible arguments you could pass this functor, f of I can give you a of I can give you a b of I, right? And it does it in a fashion that we call natural, which is related to the notion of parametricity that we have in Haskell, but isn't quite the same thing. Parametricity is a slightly stronger condition, but we let it play naturality on TV. And so we can have this category Hask to the Hask. This is functors from Hask to Hask, where the tensor that we can actually go through and we can build the product of two functors, and we can build the coproduct of two functors, and we can build those as tensors as well, and they have units, and we can proceed. But another tensor that becomes available to us in this category is the notion of functor composition. Compose fg a is f of g of a. And then the identity functor acts as a unit for composition. We can put it on and take it off on either side of functor composition. And we gain and lose no information. Okay, and we can associate composition however we want. We can go from there. So now I can finally give the definition of a monoid to a category theorist. So a monoid object is just like the notion of a monoid that we know and love, except previously what we would do is we would say we have mempty, and mempty was just M, right? It was just an object. But we really need this to be an arrow that comes from the identity for our monoidal category. So when our monoidal category is the Haskell data types with product and unit as our definition, then this is a function from unit to M. And we just throw away the unit from things in Haskell. So that's why we get mempty. On the other hand, if this was product, this would be, I take the product of M and M, and I'll give you an M. Now we're in Haskell, so what do? We curry that, just because. So we don't actually, you gotta squint at the definitions that we use in Haskell to see what a category theorist would call a monoid. Okay? And then we get these unit laws that say that we can create an M out of whole cloth on this side and go from here and there. And this is basically the unit laws that you're used to with a monoid. And this is a fancy way of writing the associativity law that you're used to with a monoid. And in the end, all is good. So, again, in Haskell, we were basically expecting to write, so our eta and our mu is that eta here is, we're going to take unit and give you empty, and mu is we're going to have to uncurry and append because we curried it. Okay, so now we can say what a monad is. A monad is a monoid object in the monoidal category of functors from Hask to Hask, with functor composition as my tensor, using identity as the identity for composition, where we have a natural transformation from identity to M. The natural transformation here is identity of A goes to M of A for all A. So we usually just drop the word identity entirely. And then you see A to M of A, that's return. And we have mu here, says that there's a natural transformation from the composition of M and M to M. So this is M of A goes to M of A. Okay, and so that's join. So we've now made more rigorous, at least, the notion of monads or monoids in the category of endofunctors. So let's go further. Here's this lovely thing I'm going to call day convolution, which has to do with applicatives. So if monads are monoids in the category of endofunctors, what the heck is an applicative? Because it also kind of lives in the category of endofunctors, and it kind of has an associative law, and it kind of has a unit. We have pure, and we have this app thing. Okay? So I could make a data type, day here, and instead of having compose FGA, I have day FGA. And this looks like I kind of took the signature of app, the app from applicative, and threw it in a blender and changed out the functors and changed out the result type a little bit. And we can make a data type that has this type, and then the monoid objects with respect to this are our applicatives, because app is effectively the thing that lets us take day FF to F. Okay.
So, what's the identity?
The identity here is the identity functor again. Technically, it winds up being the morphisms from unit. So it's unit to A. Functions from unit to A would be, unit to functions from unit, which will matter in a minute when I turn this whole thing around. So here our eta and our mu are basically this given the applicative laws. So applicatives are monoids in the category of endofunctors. What's the problem? The only difference is we chose a different tensor. We swapped one word in this original definition, and we got applicative. Now, the definition that I gave in terms of for day convolution, what we did was I want to rearrange it a little bit, and here I want to say this was comma, like A comma B goes to C, F of A, G of B. I want to write this basically in terms of lift A2 instead of app. We could have defined all of applicative with lift A2 instead of app as the sort of fundamental operation that glues together our applicatives. There's other things that we could have chosen as our way to deal with products. And so here, if we kind of uncurry lift A2, I have a tensor here, which in this case was product, and I'm going to products out here. But there's nothing here that was fundamentally about products. This could have worked with either A, B goes to C. Okay? But also, if we were working with contravariant functors, where if you had a function from A to B, I can take F of B to F of A, like where I have something like a predicate is a function from A to bool. Now you can map backwards with a function from B to A, and you'll get a predicate of B's. I can start looking for another notion of day convolution. And so one of the things that when I first started doing all this co-monad, etc. machinery in Haskell, people started asking me, well, is there a contravariant version of blank? Or, what's a cofunctor is a common buzzword, right? So if you take a functor and you turn all the arrows around, you get a functor. It's nothing new. Some people started using the term cofunctor to talk about contravariant functors, but it's something else. And so then they can ask me, well, is there a contravariant monad? The answer is no. You get this kind of weird twist, and it gets in your way. Is there a contravariant comonad? And the answer again is no. But this last summer, I was at Hack Boston, and working with James Deacon, we sat down and realized that there is a contravariant notion of applicative. And so, we get this. If we kind of squint at this day convolution thing, and we try to do the same thing that we did before with app, you can say that if you can break C up into, or if you can break A, let's do this notation, I unfortunately alpha renamed between these two things. If you can break A up into cases B and C, if you can break A up into two parts, and you can handle B's, and you can handle C's, then you can handle A's. That's what this wants to let you do. Okay? And then there's a default handler that you can basically supply that works for all A. Okay? And this thing has to be a unit for divide, just like pure winds up as kind of a funny unit for app. Okay? And here what we did was we took this sort of general definition that was in terms of the tensor in the category I came from and the tensor I'm going to, and we chose both of them to be products. And I can give you some laws. So, they're a little bit ugly. Not as bad as they're going to get. So if you give me a function, I can kind of give you the diagonal function that just kind of if you give me a value, I can just give you a diagonal function that sort of replicates that value twice. And then if we divide with the diagonal function and conquer one of the sides, it should be the same as if we just used the other thing. So this has to act like a unit for divide delta. And then there's an associative law that lets me shuffle divide deltas around. So that's the pretty version of the laws. And then we get this horrible monstrosity if you actually try to state them in their full generality, where this can be any function. So it gets uglier. But the spirit of it is the same as saying that pure acts like a unit for app. But there was nothing that really forced me to take the definitions when I was going from one monoidal category to another monoidal category. Nothing forced me to start with products and end with products. I can build another class which acts kind of like a contravariant form of alternative. And here what we're going to say is that if we can split A into either a B or a C, and I can handle B's and I can handle C's, then I can handle A's. And if A is completely impossible, then I can handle it. Okay? So now what we did was we did the same thing we did before with day convolution earlier, but we did it with, a day convolution is something that comes up rather deeply in category theory, and it's usually defined in terms of this contravariant form of thing, rather than the covariant thing. So what happened was, we squinted at applicative and we said, oh, that's day convolution. And then we said, but it's weird. Let's go write down what the real category theorists would say. And then we got this other thing. Okay? And so we found this thing. We just kind of went out there and it was just like a little piece of lost art and started playing with it. And we're going to borrow like some distributive laws, kind of like there should be distributive laws for applicative and alternative. They're not really. No one can't get anybody to agree what they are. Different alternatives satisfy different laws with respect to different applicatives. It's great fun. But I don't think I can introduce anybody in actually fixing the problem, so I'm not fighting that battle right now. Okay? So now we get this sort of little class hierarchy, which is a little bit like saying we have functor, applicative, and alternative, but we've turned the arrows around so that given a function from A to B, I can go from f of B to f of A. And if I can break A into cases that I can handle, then I can, into two things that I need to handle. I can handle both of them together and handle my A's. And if I can break A into two cases I can handle it. And if A is impossible, I'm good. Okay? So, lose is kind of funny. There's this sort of A to void, and if you think about alternative doesn't have an argument to the less than pipe greater, the M plus equivalent. So why does lose have an argument and conquer doesn't, but applicative has applicative takes an argument to pure, everything seems kind of weird. It doesn't seem to quite line up intuitively. So why is there this argument to lose? And I want to kind of take apart pure and empty and conquer and lose and put them in a kind of symmetric form. And then see why we can get rid of some of the functions and not all of them. Okay? So with pure, if we actually wrote down what the identity was for day convolution, it would be functions from unit to A. This is the identity of day here. And so, but functions from unit to A are boring. They might as well just be A in Haskell. We're not in ML. So this is A to F of A. That's why pure has the arguments A goes to F of A. On the other hand, empty here winds up with, we're working with respect to either. And so what's the unit for either? It was void. We established that earlier. So just where before we went from the unit to A, here we're going to go from the unit to A again. And here our unit is void. But there's only one arrow from void to A. It's this sort of absurd thing that says sort of ex falso quod libet, from falsehood whatever pleases, right? You can do whatever you want if you can prove falsehood. Okay? So this is trivial. This is just absurd. So we can just give you F of A. And that's why empty doesn't take any arguments in alternative. Yes?
Does it have anything to do with laziness? Because often laziness...
The only thing that had to do with laziness was the fact that I could get rid of this unit to A.
Okay.
And just go to A. Everything else here is sort of fundamental in a nice way. Conquer here says that if you can give me a function from A to unit, I can give you an F of A. But unit has this property that it's the terminal object in Haskell. And so these arrows are completely determined. Right? They're all basically const unit if we ignore people playing game with seek and doing other horrible things. So ignoring seek, this has always got no information in it. So this is just F of A. So in these two cases, there's no information here. And in this case, I got to simplify it a little bit by using laziness. But in this case, I don't get to simplify anything. A to void just basically has to be, you have to tell me that A is impossible. That's your job. Okay? So that's why lose has this argument. And why all of these things that look a little bit different to us, if we kind of, use category theory as a little bit of Vaseline for the lens, they kind of clear up and look very, very nice. All right, so, okay. So now let's look at a couple of instances. And by the way, I'm warning you, I'm going to run really long.
That's fine. We have time till 8.
Yeah, I figured. As long as you bolt the doors, we're good. Okay, so here we can have this notion of a predicate. This was the example I kind of trotted out a little bit. That if you have a function from A to bool, I can map backwards along its inputs. And so given a function from A to B, I can take a predicate on B's to a predicate on A's. And then somebody's already running for the door, just in case that wasn't going well. Okay, so now what we need is that if you can split A into a B and a C, and you have a predicate on B and a predicate on C, and you just AND together the results, we will, this will be my action for divide, and then the unit for AND is true. So I want the predicate that's just always true. And then it doesn't matter if I tried to conquer one half of, if I split my A into two A's, and then I say, okay, true and whatever I was going to get before, because it's a unit. And on the other hand, if A can't happen, here's a predicate for it. And if I can split A, and if A is either B or C, and I've got a predicate that can handle B's and a predicate that can handle C's, I can handle A. Okay? So this gives me sort of a vocabulary for talking about a bunch of things that I might want to talk about in terms of predicates. And it's a nice reusable vocabulary that's going to work for lots of different choices of monoid. So why don't we, nothing here was peculiar about and true. Why don't I just do this in general for all monoids? So there's a contravariant functor op, which is basically work over the input argument to any function. And it's contravariant, so we can map over the input, just like we did with the predicates. Nothing was fancy about bool. We can just replace it with R. And given any monoid, this is divisible. So we're just going to append our two results, and we're going to use the unit for our monoid. This is a definition for lose that's valid for any of these. Choose says if we can spit out a monoid for either one of these things, we can spit it out for either of them. Okay, so now that handled everything that's a contravariant functor from A to something. But what if we have two A's, or multiple arguments? Yes?
What do you need the monoid constraint on the lower definition for?
Because I have divisible as a superclass of decidable, just like we have applicative as a superclass of alternative. So I need it for this, and this picks it up by proxy. I'm sorry, the question was, what do I need the monoid constraint on decidable for? So equivalence classes. All right. So with predicate, we had A to bool. And with the notion of like an equivalence class, what I want is a function from A to bool with the usual equivalence class caveats, that it's reflexive, that it's transitive, that it's symmetric. We want these things to hold, right? And then now what we're going to do is we're going to borrow on, or something like that, to let us apply f to both arguments to this function. And we're going to go through and say, to do this, we're going to split our A into like an A prime and an A double prime. And we're going to split our B into a B prime and a B double prime. And then we're going to test both equivalence classes. We're going to compute sort of the product of two equivalence class structures. So if one of them was trying to break things up this way and one of them was trying to break things up this way, we're going to break it up into quadrants or something. And then if we had sort of, if A is impossible, it's still absurd. We can use the same trick to say, just throw it away. And here, the only other thing that we have to do is say that when we go to choose, if we both choose left, we use the left-hand handler. If we both choose right, we use the right-hand handler. And if we disagree, they don't match. They're not in the same equivalence class. So this is a way to use that structure that we just kind of pulled out to talk about equivalence classes. And there really will be a point to all of this. Next, let's talk about orderings. You want to give me an ordering as a data type. So we have a function from A to ordering with all the conditions you'd expect for this to be a total ordering on A's. And we can map over the arguments just like we did before. Here we're actually using the monoid on ordering. And that one's a kind of a funny monoid. So ordering has three different values: less than, equal, or greater than. And what the monoid does is it says if the left-hand argument is equal, then it takes the right-hand argument. Otherwise, it takes the left-hand argument. So it's useful for computing things in lexicographical order. It's a fun little monoid to work out on paper, why you might want to zip things with it or do something like that. And what we're going to do here is we'll use eq, because eq is the unit for that particular monoid. And the absurd case is still just as absurd as it's been all along. We haven't changed any logic there. That's kind of boring. And then to handle our lefts, if we both go left, then we use the left-hand comparator. If the first one goes left and the other one goes right, then the left one is less than our right, because it's the same case that we put on either, and gives us sort of a lexicographical ordering to our sums. If we both go right, we use the right-hand handler, and otherwise, right is greater than left. Okay? So we were able to build this up for this particular monoid as well. So these last two examples of decidable functors will be the workhorse that I'm going to be comparing something more general to. Because I want something that's going to work a lot like breaking things up into equivalence classes. And I'm going to want something that's a lot like doing comparisons on them. But we're not going to work pairwise, because everything we just did was working pairwise. So what I wanted was this sort of vocabulary for talking about things, for how to split things apart. And these are good working examples to kind of build up our intuition for what the heck it means. So now, we're going to go a little bit further down the rabbit hole. And we're going to go play with GHC generics for a second. And if you're not familiar with GHC generics, then you can probably skip this slide and just look at the next one and say there's magic in between. But what we're going to do is this. If you have any abstract data type in Haskell, it's made out of effectively sums and products and some other bits. Okay? And so what I want to do is I want to tell you, if you can tell me how to handle all the leaves in there that are not made out of sums and products, I'm going to use a decidable instance to handle the sums and the products and the units in there. So I'm going to try and supply you some generic plumbing for how to consume anything you want in Haskell. Okay? So here what we're doing is, when we have something that looks like a product, it takes on this form. It uses a slightly different symbol than the comma because this is on the functors. If you give me a unit, we're going to conquer it. If you give me a sum, we're going to break it into sums and we're going to choose our way through it. And if you give me something that doesn't exist, it's not possible. And so what the heck can I do with this thing? So I put a little wrapper on top of that, and I call it deciding. And I make a little type alias for all the constraints that balls up. And so the end result is this. If you give me some kind of proxy that tells me what the constraints are I'm going to need at each one of the leaves, and if you can, given that constraint, you can give me one of these contrarian functors that can handle B's, I can handle any structure that is made up of all leaves that I can handle that way. Okay? And so now what we have is, like, if I wanted to build a generic version of compare that worked over any tree structure using GHC generics, and then use that boilerplate that we built earlier for handling comparisons, then what I can do is I can say, hey, deciding, at the leaves I'm going to need an ORD instance, and given that ORD instance, it's possible for me to call the compare function. I can wrap that up in this constructor and give you a comparison on A's if I have ORD on A. So now I can handle the leaves. This thing deals with the entire tree to get me down there. It deals with lexicographic ordering on anything that looks like products. And it deals with lefts come before rights on anything that looks like a sum. So if you have multiple constructors, the earlier constructors come before the later constructors. And by the time we're done, we've built a thing that does generic comparisons on whatever ADT you have, as long as it's GHC generic and all the parts are sortable, are ordered. We can do the same thing for equivalence classes. We can do a generic equality that says, given two A's, I can tell you whether they're equivalent, as long as the leaves can be compared for equality, because given eq of A, I can give you the equal function. And we can just bubble that up and call it an equivalence. Okay. So now we're finally able to actually talk about the domain I care about. Sorry for the 43 minutes worth of preamble. It's a little bit of a warm-up. Okay. So the topic I'm interested in talking about is this notion of stable ordered discrimination, which was what Fritz implemented as sort of the first of two things in his discrimination paper. And he built this lovely little data type that is very simple. And unfortunately, it's an instance of basically none of the classes that I care about. So I'm going to switch it to this more complicated data type that is an instance of everything. Okay? So here's the idea. What I want you to do is give me a list of pairs of A's and B's, where B is anything you want that you're just going to pass me. And what I want to do is I want to break this thing up into equivalence classes by A. Okay, sorting them by whatever criteria I wanted to put on A. And I want to give you back the members of each equivalence class, ordered by the way that I've selected them.
Are there any constraints on A?
That's up to you. This is a sort, it's a data type. You can make any instance you want of this, right? As long as you break these things up into some order that just depends on the A, right? So you can gather up all the things that share whatever property of A you want.
This is a bit like sort of,
So,
as in the A is possibly
Yeah, you can think of this almost like a Schwartzian transform or something on your B's. You've got the pair of the B's and what thing you actually want to sort by, right? But you're not necessarily using the ORed instance on A or the equivalent of the ORed instance on A. It could just be that you have a thing that takes all of the B's and puts them in one equivalence class, right? It just takes this thing, maps second over this list, gives me a list of B's, and gives me a singleton list that consists of that entire list of all of my B's. That would be a perfectly admissible sort.
So the only thing we care here is that we have not too many classes of equivalence for A.
Yeah, the only thing we care here is that we don't have too many classes of equivalence for A. What I'm trying to.
I mean, we probably don't want to have like A to be just float and having.
I'm perfectly willing to have A, B float and discriminate on every individual float. We'll deal with that when we get there.
But you do have properties. I would expect that you're not allowed to duplicate or forget about B's.
Yes, correct. We have to use we're only allowed to break these things up into equivalent classes by some criteria on A. We're not allowed to forget B's, and we have to give back these B's within each equivalence class in the order they come in the list. So this has to be a stable discriminator. So there's a number of these little side conditions that we're all gonna try and preserve as we go. Okay. So we're going to try and do this sort of final encoding of this particular problem. And my goal here is to sort of improve the code for discrimination by switching from this initial solution to this final solution. And what we have here is the contravariant for sort. A only occurs here in negative position. It's only ever an argument to something. So we can map backwards over it, just like we could with predicate. It's kind of buried under a couple of functors or something like that, but we can still map backwards over it. So you give me any function from A to B, and I can take a sort of B's to a sort of A's. And then we have these sort of divisible and decidable things that we have to implement. But if we have that, then I can make a class sorting for things that I can sort. And as long as I can decide sorting at the leaves, I can sort my A's. They're made generically out of whatever the pieces are. So you give me a sorting, this just tells me that sorting is going to need sorting, the class, in order to be able to be called. And then just go. You can just write instances without actually writing any bodies. So if we have those two definitions, or the two class definitions, for divisible and decidable, all of these instances write themselves except for the hard ones, like I want to deal with int and stuff like that. And then the trick is showing that none of these things destroy the asymptotics of the resulting algorithm. And then we can get all of this stuff in linear time. And the particular law that I want to stick on this class is a little bit stronger than the ORed class, and it's a little bit gratuitous that I'm putting it on there. But what I want is this. If you give me any strictly monotone increasing function, f, I really want that contramap f on sorting is equal to sorting. So if you give me a monotone function from your inputs to your outputs, then this is a sort of requirement that my sorting is structural. And that's stronger than ORed ever claims, but I want it, so I'm claiming it. You can throw that law away, but it motivates something later, that I want this law for sorting and a related law for something else. Okay, so now let's talk about divisible. Divisible was that we had divide and conquer, because I needed applicative names, and co-app gives nobody any intuition for anything. So what do? Conquer says put everything in that one equivalence class that I used as an example earlier, that we could just have the thing that gives us no information. And then divide has to do something tricky. What we're going to do is you've given me an A and some payload worth of information that you want about each one of these things. And I want you to break A up into a B and a C. Now we're going to discriminate with the first discriminator using B and C comma D as my payload. And that's going to break things up into this sort of list of B's. Then I bind that into the second discriminator, and that's going to discriminate on my C's recursively. Okay? And that is as you work it out, it won't actually change the asymptotics. Each one of these things was linear in the number of elements that it was dealing with. And so I leave that as a fun exercise to show that this didn't actually ruin any asymptotics. So we can divide these things. And we can do this decidable piece as well. We can choose and lose. So lose says that if A is impossible, then just map down this list, and anything that anytime you find an A, you're good. That whole case was impossible. We can run this on an empty list, and that's perfectly fine. So it's a little bit more refined than the previous cases where we were dealing with absurd. But here, if the list is inhabited and there's any A's in it, then something went really, really wrong. And on the other hand, to choose between two sorts, we have to break ourselves into our lefts and our rights. So we're just going to run through the list here, and then take all the lefts and run them through the left discriminator, take all the rights and run them through the right discriminator. And we're just going to append these things. So we're going to put all the lefts before all the rights. And then the last thing we really need is sort of like a sorting for integers up to a number n. So you give me a thing and I'll sort an array of n. I'll sort integers that are at most n. And then if I have this as a building block, which is like go do computer science, I guess 201, it's not quite 101 material, like do a Radix sort, I can then go through and say, we're going to sort word 8s by using 256 buckets. We're going to sort word 16s by using 65,000 buckets. As we get bigger, it's going to get a little bit trickier, because each one of these things, what was happening was, when I did that bind, this was effectively doing that American flag top-down style. What it was doing was, it was sorting the most significant thing, what came first in my pair in order. It did the most significant bits, basically, and then the least significant bits by recursively breaking them down, right? Well, when I go to deal with larger integers, I'm always going to have, it's probably better for me to deal with 4 things from the bottom up than it is for me to deal with lots of little sorts from the top down. So instead of doing the American flag style sort, I actually want to locally do a Radix sort. So here, to do the word 32 case, what I would do is, I'm going to do the 65,000 case twice, but I'm going to break it out into the least significant bits and then the next most significant bit. So I'm going to divide into the less significant bits and then the more significant bits and then discriminate that way. But it's better for me to go through and do something horrible to build a Radix sort, where what I have to do is sort of work my way up through from the bottom to the top. And what we're going to do here is we're going to do exactly 2 sorts, rather than a lot of little sorts after one big sort. Yes?
Is the instance for, what is it, divide? I think the one with the bind. Are you forced to pick the first element as the first discriminant, or could you pick the second element first?
The first element is the first discriminant.
If you go down back a little bit, more. So here you pick B, right? You
Yes.
B, C, D. Could you pick C first?
I could have, but I would have gotten a weird order, right? You would have read with a thing that was different from what ORD was going to try and do. It would have been basically using dual ordering instead of ordering.
Would it be a legal instance for this?
It would be this thing doesn't care, if I recall correctly.
Okay,
You might have to, I don't know if you'd have to flip the either case as well.
My question is, do these is like when you're talking about the performance of the states?
Mhm.
I'm assuming that this implementation choice matters, right?
Well, this is the only implementation that we have here. We don't necessarily have the ability to do the Radix trick without changing our asymptotics. Because we're going to see something that I had to do in order to make the Radix thing work. We did American flag, we went top down, right? In order to make the Radix thing work, I'm going to get kind of a wrong answer, and then I have to fix it up. So I have to go through and sort of group these things up into runs manually, where runs goes through and I've flattened this whole thing down into just a list of B's, or a list of actual ints and B's, where those are a list of word 32s and B's. So I've done this whole thing. I've sorted it, but I didn't wind up with a list of B's. I just wound up with a list of word 32s and B's. I left my original word intact here. And then I have to go through and break them up into runs by that. So this adds a little bit of an annoying step at the end of it, but as a result, it wins on the wall clock. So Duncan would be proud. And now with that, we can go write a couple of functions that people like. Sort. So to sort a list of A's, what I want you to do is run sorting for my A's. We're just going to break A. We're going to take each A and we're going to discriminate on A, and I'm going to give you back the A. And then concatenate all those little sublists. And that is sort. And sorting on naturals was linear time. Sorting on sums and products doesn't affect my linearity. So by the time we're done, we will be linear in the amount of the ADTs that we have to inspect in order to break all of the ties. So in the size of the input that I need to look at in order to discriminate will actually be linear. We can do sort with, which is sort of a Schwartzian transform thing, where we're just going to, you give me the function on what you want to sort about, and well, this is sort is just sort with id. So now let's do something more fun. To map. So map has a from list method that's n log n. So if you had a stable ordered discriminator that was compatible with your ORD instance, then what you can do is you can just sort using that, take each equivalence class, take the last member of it, because that's what from list is, or from list will do, and then use the map from distinct ascending list combinator, which expects that we only ever give distinct elements, and that we give elements in an ascending order, and that's linear time map construction off of this machinery. So if you have any data lying around that you need to build maps out of, which sometimes happens in Haskell, this is a kind of a nice way to go about building your map, because we get rid of a log n factor. Yes?
But if you have a recursive data type, right?
It works.
Yeah, but I mean, would it still be constant time?
It's constant time in the amount of that data structure it has to inspect.
Right, but I mean, right.
That's, if you think about it, that's still it's a constant in a different thing, but it is constant. It's linear in a different thing. I'm sorry.
Yeah, I said constant, but I meant.
Yes, sorry. So the question was, if you have a recursive data type and you have to keep exploring down it in order to find these differences, is it really linear? And the answer is that it's linear in the amount of the structure you have to inspect. Whereas a normal pairwise comparison is going to do that same kind of, it's going to have to walk down those elements anyways to compare them. So it's got the same cost. They just vary it in the cost of their comparison. It's n log n times that same cost. Except now they have to pay it multiple times because they have to inspect the same elements in different ways. So it's actually worse in the normal comparison case. So I actually win there too. Why not? Okay, so the end result here, or for this first phase of the of the solution, is that now we have on time stable ordered structural discrimination for any ADT that we want, and using the Radix sort on instead of American flag sort on our integers, let us sort of speed up a little bit over what Fritz's code does. By using this sort of more generic class framework, we're now instances of all the things. You can sit there and contramap over these things. You can do whatever you want to work with your discriminators. Whereas with the original implementation of this that kind of comes from the paper, it really wasn't terribly Haskell-y in the sort of modern Haskell sense. Like there were no instances. Everything was sort of a one-off combinator for working with this particular data type. And you kind of had to make it up as you go. You made up your own rules. But here we can kind of borrow our intuitions from what ordering does and what comparison does. Or sorry, what equivalence and what comparison does. So next, what about unordered discrimination? What if I don't actually care about the order in which I get my equivalence classes out, just what things are in the equivalence class? So, Fritz has a solution there. He builds this lovely little data type. And we'll go for this slightly more complicated one. So this data type is probably wrong. And so here's where I'm actually going to turn this into more of a call for help. We're gonna go through the pieces that I know of what we can do here. We can go with what's wrong with this, and we're gonna go to what I want. And people are welcome to reach out and help me. So why do I care about unordered discrimination? Well, we have an eq instance for IORef of A. This should be an IORef of A. But there's no ORed instance for IORef, because IO references are just like a place in memory that's got a pointer in it that points to something else. And so we can discriminate, or we can compare for equality two IO references to see if they actually point to the same object in memory. Or not that they're pointing out to the same object reference, but if I changed one of them, I would be changing the other IO ref because it's the same IO ref. And I can't put an ordering on that because these things move around in memory. Now, people, in general, if they need to do something like that with an ST-ref or something like that, they just build their own little monad and they make a variable supply and they pair up their ST-ref with an integer. But now you always risk somebody going through and saying, well, give me all ST-refs less than 4,000 or something like that. It just doesn't, you get operations that don't make sense under the semantics that we want to assign to references. Like the fact that pointers are numbers, but you do all sorts of weird comparisons with pointers that don't really make sense in a garbage collected setting. So it'd be nice to have sort of encapsulation that avoided us ever saying anything bad, but let us, discriminate references in linear time. Because the problem is, right now, to discriminate references, I only have pairwise comparisons for equality, not even for ordering. And given that, the best I can do is theta n squared. I can't do better than n squared by any pairwise comparison means that only compare for equality. So to do sort of grouping for naturals, what I want to do is I want to hack up a Radix sort. And instead of a Radix sort going through and gathering all the buckets in order, what I'm going to do is this. As I go to put a thing in a bucket, if that bucket was empty, I'm going to thread the bucket itself, the number of the bucket, onto a list of all the buckets I've seen so far. Okay? And so what I'll get is I'll get my buckets in the order that I encounter them. And then what I can do is I can kind of twist that whole list around and then gather up the buckets in the order I saw them. And then for at least the integer case, I get the fact that the equivalence classes aren't going to come out in any sort of intrinsic order based on A, but instead on the order in which I first encountered the A member of that equivalence class. And so making this thing tricky is a little bit, or making this one efficient is a little bit tricky. So Fritz has a slight variation on this theme, but by the time we get done with it, we wind up having to do unsafePerformIO inside of unsafePerformIO in order to make something that actually runs efficiently. Okay, so what we're going to do is I need to make these slabs of like 65,000 buckets. And I could naively go off and do this in like STRef. I could make an ST array that had 65,000 entries in it, all of them were empty lists. I'd go mangle, say 10 of them, or something like that, however many I need for my particular discriminator, and then I would go through and grab all the individual entries out of each of those buckets, reverse them, and spit out my answer. But now I did all this work to set up this gigantic array, and then I waste it by throwing it away. Duncan would not be happy. Sorry, you're the boogeyman right now. On the other hand, what I can do is this. I can maintain like my own free list of these buffers of this size. And then what I'm going to do is I'm going to go to try and grab something off the free list, and if there's one there, I'll just take it, and I'll unsafe coerce it around. And everything that's on the free list always has empty lists in it. So it's okay for me to convert an array of lists of A's to an array of lists of B's, as long as everything in the list, everything in the array is nil. And then I go through and I visit everything, const onto my list, and then I take the list that I have, reverse all the elements of each one of them, spit out my answer, and then I return my list to the free list, having restored all the nils that I touched. So it's kind of horrible, but it's really fast, and it works. So I'll take it. So without this, we don't win on the wall clock ever, right? With this, we can beat like a quicksort implementation. So those are the kinds of, the motivation here is that you need something horrible like this for the stable, unordered case in order to actually start winning. And then I have this law that I want, which is that if you give me any injective function, I should be able to conjure map that over grouping and get grouping. That should be equivalent. You shouldn't be able to observe a difference. And this is where the problem comes in. But I mean, why do I want this law? In many ways, I want this law because with it, it's possible for me to say that these things could be productive. And that would let me have a nub that was an online nub, but now runs in ON time instead of ON squared time. Now we have an online nub that we can write that's like ON log n time using data.stat or the like. But that now needs an ordering instance. But what about things I can't order, like IO refs? I can nub a list of IO refs, but I can't put it in order and then run it through that thing. And I want to be able to do like a version of group. And in group in Haskell today goes through and just only looks for things that are next to each other, that are the same, and then gathers all of that up into a group and then moves on to the next. But what if I wanted to be able to do sort of group at a distance? We can get a version of group that uses this notion of a grouping. And there's theoretically a potential for streaming here. Because if I wanted to run grouping on something like this, and let's say I was just grouping them up by integers, here I'm going to say, the moment I encounter this first equivalence class, I know that the payload that we're going to put here is going to be an A. And I don't know what the rest of this list is. I don't know if I'm done here, if the string will end. And I don't even know if I'm going to have any more equivalence classes. But up until here, I'm good. So if I were to look at the result, I could see that A, and I'd be making progress. And at the moment I see this next element, then I know this. I know that this next element is a list that starts with B, and I don't know what's the tail of it, and I don't know if I have any more lists, but I at least know that much. And when I see this next element, now what I've done is I can make this thing strict. I can start forcing this thing. So it's this weird thing where it's kind of like laziness, but what's happening is we're sort of creating a promise that is, I will tell you what the tail of this list is eventually, and then fulfilling it on demand. So you could build a monad in which you could write this, and that's actually one of the sort of open issues that I have here is, how do I build like a nice little ST-like monad where I can create promises and fulfill them, and give you back the result where the promises can now reference the new promises that I'm making forward. And that when I go to look at a promise, what it'll do is it would run this entire computation up until it fulfills that promise and then puts it back to sleep. Like it basically puts it back in the box until somebody else comes along and says, hey, can you please run your computation further until you get to another promise? Okay? But with that, then grouping could be entirely productive, which means that nub would be an online operation. Okay, and that's something that goes above and beyond what Fritz's papers do. I mean, and the trouble with that law is that if we look at the actual paper that backs this, then unordered discrimination, which is defined in a notation that doesn't use the classes, it actually just builds a combinator that walks over that ADT we built before. So we build an interpreter for a simpler ADT. There, its sum handler goes through and breaks things up into lefts and breaks them up into rights and then appends them in order. It's not passing my law. It's doing what we were doing for the sorting case. But the problem is the moment you do any sorting, we're dead in the water when it comes to productivity. Because I want to be able to spit out the results of nub online as I go. But let's say that I wanted to nub a list of Booleans. And I had an infinite list of trues. Okay? I'm not ever going to be able to emit that first true because what's going to happen is the false, it's going to try and put all my falses before all my trues. And I don't know that I don't have any of them. right? So I'll just starve trying to give you an answer. So I'm not sufficiently productive. The moment I do any sorting, I fail. Okay, now, for many cases, we don't actually care. If I just wanted to do that grouping thing like that, and I didn't actually care about the ordering that I got my answers out in the end, then I would be perfectly okay with this instance. And then also, when we go down to deal with these products, what's going to happen is, we're going to get our answers are also going to get all jumbled together. So the product case is also wrong. So that's why I was saying when I pointed out the type for group, maybe the type that I gave for group there is wrong. And we need to do something more like a stream fusion thing with skip nodes, where instead of like doing just a blank skip node, we tell you which equivalence class I put a thing into and then juggle it upstream. I don't have all the answers there. I can point to you as far as we've gotten and how far I think I can go with this and where we think this can be interesting. And there's a fix that at least gets us the correct, it's the ordering that I want for that law. We can go through, and what I can do is I can take and like zip with every element the number that is its ordinal position in my original input. Then I can go through, run my sort of unordered discriminator using those additional classes, those implementations that we had before that were a little bit naive. And then I can finally go through and sort using the position of the first element of that equivalence class that I saw. This uses the fact that we're still stable, even if we're doing a little bit of sorting when we shouldn't be. And this would give me a correct answer, but because it had to do a sort internally, it can never be productive. And we can fix the sum case pretty easily. We can go through and do what we just did there, where we tag everything by the order in which I encountered it. Basically, I'm just going to zip up all of my things with a list with a number, which is its position in the list. And then I'm going to go through and do this sort of mix operation that's going to go through and try and run through these lists of equivalence classes, and then look to see which one of them came first in the input. And it's going to do sort of a merge of a merge sort. It's going to merge my set of equivalence classes. So we can do this. And that will fix our sum case, but it doesn't get us the products. The products are more interesting, and that's where we start talking about something weird. And I am open to suggestions and patches.
So does this fix your list of booleans or list of truths?
This fixes my list of booleans, because what will happen is we're going to choose between lefts and rights, and it will do the right thing. So nub will now give me true and then starve. Yay. I'm sorry, does this fix my list of booleans was the question. So now I want to talk about something weird. We went off into category theory for a while, then we played around with some algebraic data types. I want to talk about another weird corner of optimization in Haskell, which is the notion of we can build custom foreign prims to do things that we want to do. And let's say I wanted to do groupings for ST-refs. The problem with ST-refs before was I can only compare them for equality, right? Because they can move around behind my back. So I want to build this sort of custom primitive that is responsible for doing, well, it's going to have to take an any, because I don't actually have any other way to pass an actual strongly typed Haskell data type to a primitive. So a custom foreign primitive is this. GHC itself compiles down from Haskell, the surface language that you know, through this thing called, through core, to this thing called the spineless tagless G machine, down to this other thing called C++, and then from there it goes to LLVM, and then it spits out assembly. You know, just a couple passes. That C++ thing can be written by hand. Okay, Simon Marlowe has actually given fairly recently a fairly nice syntax for working with writing our own custom C++. So, in order to discriminate ST-refs, which I can only normally compare for equality, like pairwise, I'm actually going to have to get in there and keep the garbage collector from moving them around while I compare them. And so in order to do that, I'm going to have to first make sure that my list is entirely strict, because I can't have to do any allocation, because if I have to do any allocation, I can be forced to do a garbage collection. So what I do is, the first thing I do is I run through my list of ST-refs and I force it all the way through. So I know that I have a list of things that have already been forced. Then I call my little custom, then I make sure that I have a mutable byte array that is as large as I need to hold all of the addresses for all of these strefs. Then I call my little custom prim and get an answer, and then I freeze the resulting list and match the addresses that I've scribbled into the mutable byte array and into my original list, and then I discriminate on addresses, which are like 64-bit pointers. Okay, but now they're just 64-bit integers, and I can move things around after that, after I've pulled out all their addresses. So we can build this horrible thing, which probably doesn't show up at all on the slides, but what it's doing is, it's this little C-like dialect where every allocation is very explicit, and instead of where we would normally jump into a closure, what I'm doing is I'm just trying to figure out if there's an indirection and then sort of looping back. So this is done completely without allocation. It goes through and walks that whole structure and sort of bangs out the addresses into my mutable byte array in a tight loop. Now this is terrible. We're stalling the entire garbage collector while this thing runs. Simon Marlowe was very, very wroth with me when I mentioned to him that I could do this. But it works, right? So it's a thing. So if you ever have to discriminate a lot of strefs and you can't bring yourself to make that little integer tag that goes with it, it is possible to discriminate strefs or IORefs or mvar or a whole bunch of other things in linear time. And using some machinery from the paper, you can actually use this for like if you have bags or sets of these things as well. Okay, so I'm going to leave that to the actual to the paper and the code. Okay. And then I have one last use case. So I did tell you I was going to run long. I'm going to be about
It's fine.
5 more minutes. 10 more minutes. Yeah, 10 more minutes. 15. Anyways. So the next thing is occasionally I don't actually care if I have a stable, if it's ordered or an unordered discriminator. Sometimes it's just get me answers in some equivalence classes, right? So if we really want some kind of thing that I just like discriminate on it, like, you know, and say run sort or run group, no matter what it's going to be, get me out my list of these. And now I want to talk about how we can do table joins, because table joins are one of those things where people are used to having to come up with a schema where they have to sort their data in the right way, and then they hope that they can query it. And then every once in a while, you have something that you have to take out of your relational store, and you have to process it in memory. And what do? You come up with these sort of horrible little schemes where you hash this against that, or you sort this against that, and you try to do your own joins, right? So what I want is a join that is just linear time. You give me a discriminator that you want to use for the thing you want to join on, and I want it to just be linear time. Okay? So let's do a join. This I've stolen from Fritz. And what we're going to do is we're going to join on whether or not our values are even or odd, just to make it interesting. So it's not actually joining on the integer. We're going to just join on the evenness or the oddness of the integer. Okay? So you could contramap even over your over the discriminator for Booleans, and you'll get a contramap for even or odd, or you'll get a discriminator for is even or odd. So what I want to do is this: you've given me two tables. One is like we've got a list of keys, 5, 4, and 7 with values associated with it. Here we have another set of keys with different values associated with it. And I want to join the two things together. Okay, I want to join all the evens over here with all the evens over there, and all the odds over there with all the odds over there. So what we're going to do is I'm going to inject these by tagging them with left, and I'm going to inject these by tagging them with right. Now, we append these two lists together, and we feed them to our one discriminator on is it even or odd. The result will be, so we've got this list here of all the lefts and then all the rights. So all the lefts come before all the rights. Now, once I've discriminated, I'm going to get all the things that were odd and then all the things that were even as two different equivalence classes. Now what I have to do is break this out, take all the lefts and all the rights within the same equivalence class, and take their cross product. Right? We've already broken them out into equivalence classes, and now these will be a full cross product. Okay? And when we're done, we have done in linear time, in the total amount of input and the total amount of output, we've done a join. And why I care about that unordered discrimination case that I was just talking about is I want to be able to start spitting out results online. I want to be able to start giving you, the things that you want to group out of this as you're feeding me input still. Not after I get all the input. Because right now, in order to do this, what I have to do is I have to get all of the input, then I can discriminate it, and then I can start streaming results. You get no answers until I'm done. So that's why I care. And so, what did we have here? We had the fact that we were using a stable discriminator. So all the lefts in the result, in each one of the equivalence classes individually, are going to come before all the rights. So I need some kind of span that's going to take out the lefts and the rights. It's going to take a list of eithers of A's and B's, and it's going to give me a list of A's and a list of B's. These are all the lefts and then all the rights. And we can do this in CPS style, and Duncan will be mad at me. Because there's all sorts of closures being allocated here, and it's a little bit slow. I don't know how to do it more efficiently though, so. And then we can do outer joins, like a whole table at a time. So here what you're gonna do is you're gonna tell me this. If you have any discriminator, ordered or unordered, and you know how you wanna merge out an entire table of A's and an entire table of B's to give me something we'll call C, and you have a selector that knows how to get the column that you're interested in on the left and the column you're interested in on the right. Give me a left table and a right table, and I'll join it and give you the final result. So you might just use app here, and you'll get or you might do app or lift A2 comma or something like that, and you'll get the product table, and you'll get each one of them grouped. And we can do inner joins, just by kind of handling some of those cases for you. So you tell me how you want to match the two rows together instead. And then what I'll do is, if either one of the input lists is empty, then the inner join there will be empty. And we'll spit out the result. We can do left and right outer joins. All of those things fit into this framework. So again, the open problem that I have here is that I really want this form of productive, stable, ordered discrimination. So I really want this...
Ordered or unordered?
Did I say ordered? I say productive, stable, unordered discrimination. Because it's going to need a better version of grouping that and a better version of divide. We've done... we did divide. We did... Not divide, we did decide, but we didn't do divide. And then it likely needs a different encoding, and there's some sort of lazy ST-like monad with IVARs that should exist, that we can kind of reason about from just sort of what it has to do. And we can't afford to make it so that each one of these things is just a thunk that forces the whole list up to a given point, because that would require us to traverse the list many different times. Each one of them is going to try and zoom along the list. So it really has to be this sort of spooky action at a distance where one of these things is fulfilling a promise that's for a portion of a data structure that's elsewhere inside of our environment. So, in conclusion, only a half hour long, we have discrimination giving us ON sort, nub, group, inner left, right, outer joins, etc. And that worked basically for any ADT you want. It works for integers, it works for pointers, because we can do this thing with references. So what else do you really want to be able to discriminate on that I can't? And that's a question that you can come up to me with later. And regardless, the code is up on my GitHub. You can go to Kmett discrimination right now. As soon as we figure out some way to do this productive or unordered discrimination thing, I'm happy to put it up on Hackage. I may put it up on Hackage earlier just to get some more eyeballs on it. And the documentation, you can actually just go to the GH pages link that's available on that GitHub account. And again, I really want this form of productive unordered discrimination. Please help me get there. Thank you. Are there any questions?
Does bucket sort have a bit of a problem with very small lists? That's sort of the constant.
Does bucket sort have a problem with small lists? Sort of. The sorting case, the real bucket sort does, right? Because you have to create and use all those buckets, right? So you have to walk that whole list. And there's little games you can play to try and speed it up by keeping track of, is there anything used inside of this block, and change the, unfortunately, changes the asymptotics to sort of log in, right? So there's ways to try and make it faster. One way to do it is to just use a lot fewer buckets, right? If I choose 256 buckets, my constant factors go down considerably relative to the 65,536 buckets I'm using here. I have not tuned those constants in this case. So the usual answer is you just use smaller buckets and you use more passes.
But then it would be such that the linear time has to be taken with a caveat.
But let's think about it. What happens is I have to do 8 passes, each of which are 256, versus 2 passes that are 65,536, right? It's a pure win when you have a smaller number of buckets, until you get down to some grain size that's too small.
This I understand. It's just, to me, it sounds like, well, you should always use that. I have a feeling that for short input sequences, so for short amounts of elements, standard standard comparative sorting might actually be better.
And so the question is the observation is that for short input sequences that standard log n style sorting is probably a win. I don't have a good benchmarks in the small. So it's more that there's an interesting point here in the design space that scales indefinitely. And how small it scales is another question. It's interesting, though, that I haven't found anything that actually tries to get down to a small grain size and then internally do pairwise comparison sorts. So I don't have good comparison literature on that.
Another topic is how does this work when you go to external memory?
How does this work in external? Well, where would we run into a problem? I'm trying to think.
Well, I mean, it assumes that you have low latency and random access, which is not really true on the current hardware.
What am I doing that's random access? I'm using random access for my buckets, right? But I'm not using random access for my data. I'm walking through my stream one after another, after another, after another.
Okay, I agree.
Putting things into buckets in small ascending order, and then getting tighter and tighter groupings that I'm twisting on. So I actually work pretty well for all my caches. Yes?
So what is the difference between, in terms of memory usage, between a pairwise sort and a linear sort?
So what is the difference in memory usage between a pairwise sort and the linear sort? So there's variations on this. The original American flag sort was an unstable sort. Not what I've got here is sort of like, Haskell quick sort isn't really quick sort. This is sort of American flag sort that isn't really American flag sort, right? So the original version of this, that was of American flag sort, was an in-place sort. Okay, so and in that sense, and there's in-place quick sorts that do, of course, get the same bounds. So it's a matter of, well, are you fiddling with a stack or something like that? So it's not an appreciable win either way. Now here, what I'm doing doesn't really lend itself to in-place, so I'm probably wasting a lot more memory than a nice in-place quick sort would or something. But in exchange for that, I'm also getting different asymptotics.
Yeah, it's a trade-off. You lose memory.
Yeah, so we lose memory, but we gain speed. Questions over here?
Is there any reason why would you need grouping for pointers? Like, basically you have to force them all, so it doesn't matter if you use sorting.
Is there any reason why I have to use grouping for pointers? Grouping is faster. Because the trick that we used there that only visited the buckets that I actually touched, what wins? It's sort of the story behind why we want to do grouping for pointers. And the other thing is there's a sort of deeper mystery there. I turned them into a bunch of integers. but the integers are going to be different from run to run of that function. So the ordering would be completely random, and it's not really a pure function. If I share the result and use it, it's not going to be the same answer I would get from calling it twice, right? So there would be an abstraction leak, that you could see that this thing is doing something weird behind your back. Whereas with the grouping, even though I give you completely different addresses for all the pointers, they all wind up in the same equivalence classes, and I still put the equivalence classes out in the same order. So the result of the function is actually stable, only for the unordered discrimination case. Yes?
So when you have a data type, let's say data D equals A or B or C or D, and at the level where you're doing your sorting, you want to do this as some kind of bucket sort. But then when you write a generic instance, because in the generics instance, these alternatives are expressed as pairs of plus, right? Are you not also always working on just two buckets, in the left and the right one?
So the question was, if I had like a data constructor like A or B or C, or if I had a data type with several constructors like that, and I wanted to treat it like a small number, isn't this effectively a sort of two-way American flag sort? And the answer is yes. We're effectively, at each point in time, we're forking to count our way down, and we're working bitwise.
So if we just did this would just occur a constant factor depending on the size of the alternatives, right? The number of alternatives. But you could probably flatten it out in some way, right? If you walk it first, and then you could like...
So if you flatten it out, you could then do a single bucket, right? And so you can supply your own discriminators. You don't have to use the ones that I get by generics, right? So when you define the instance, what I gave you was a default definition for how you can get a discriminator. There's nothing that prevents you from going through and saying, hey, look, contramap from enum or to enum. I can't remember which way it's going to go. It's contravariant. Ow. Okay.
So the best case in this case would be if we had an enum instance that is known to be compact with integers, right?
Mm-hmm.
And then we could do that really fast.
Yes, if we had an enum instance that was compact and we had min bound and max bound, we can kind of shift by the max bound to put that at 0, take the difference between them, and as long as it's compact and well behaved, we're nice. All set.
Maybe this flattening with generics SOP, you can probably do the flattening quite nicely.
Yes, with generics SOP, you can do the flattening with the sort of the sum of product stuff that.
Yeah.
So those options work. There's plenty of other generic solutions in the C. GHC generics is just sort of supported out of the box.
Yeah, it's always two buckets, apart from the leaves that are coded to int or like for ints or words or.
Yeah, we're always splitting pairwise.
It's always two, yeah.
And there's potentially some interesting things that have to do with trying to do like a product that acts like your tag, and then sort of do a dependent step for the next layer of the system. So there's some things that kind of relate to sort of tagging and the C4 thing that we can talk about offline.
So the question, why is it called American flag? Do you know?
So there was a puzzle, a problem that I think Dijkstra first talked about, which was the Dutch flag problem, which is you're given a bunch of balls that are colored like red, white, and blue. Okay, and what you have to do is you want to put them in the order of the colors of the Dutch flag, and I'll get them wrong, so whatever it is. And then what you have, so one way to do this is that you can kind of like run through all of your buckets and just count up how many you have of each type, sort of look at the prefix sums over that, and then what your goal is to go through and grab the first ball and put it in the right bucket. And that's going to displace a ball and put that in the right bucket. And just kind of keep track of this sort of high water mark as you go through it. Okay? So this was done with 3 colors to begin with, or 3 different bins. So if you had lots of different things, you'd have something that has more stripes in it, like an American flag. So that's where the name comes from, as far as I can tell. All right. Oh.
Yeah, I'm just curious about that. There was this divide type class. Is it something you could use to, like, I don't know, create some form of generic parallelism, like creating sparks or stuff like that? Or?
Is it something I can use to create a sort of generic? I didn't follow the last.
I mean to do like, you have the parallel connection where you can just go par and you could divide
Right.
Oh, can I do something like parallel collections or
Yeah,
something
exactly.
like that? So you can use it to consume a lot of things. There's also, what's another good example? So you can actually build an example that goes with that is like you can build a notion of like NF data, right? NF data itself, if you think about it, is that you give me an A and I'll give you a unit, right? That's what happens with RNF. So you can make a sort of generic RNF as well, right? Using that same thing, you'd have to make a contravariant functor that can handle sums and products and do the things. It's just A goes to unit, and that makes my statement earlier that A goes to unit being trivial makes that a lie. But if you had that, then you can do something like NF data or something like that, right? And then you could perhaps do par-like things inside of that, or break things up into bins. But for that and for work scaling and stuff like that, I have not tried it in that domain. All right. Oh, yes.
Once you have a productive unordered discrimination, you think you could wrap it into an iterative.
So once you have a productive unordered discriminator, do you think I could wrap it in an iterative style design? Very likely. The trick is that the intermediate steps are going to be weird. But then that final output can probably be just sort of online. You feed me more input, and I keep feeding you output. So it can be like the more modern parsing combinators and stuff like that, where there's not you give me a string, it's that you give me continuations to feed me more. So iterative style, yes. All right, I think that's enough. Anybody wants to grab me offline, feel free. I'm happy to talk about this stuff pretty much incessantly, as you may have noticed. So thank you.